Welcome to the 38th lecture on computational mathematics with SageMath. Let us continue exploring some more concepts in inner product spaces. So let us define what is meaning of an orthogonal set of vectors in an inner product space. So suppose V is an inner product space and S a subset of V containing vector v1, v2, vk. This could be infinite subset as well. Then we say that S is an orthogonal set if inner product of Vi with Vj is 0 whenever I is not equal to j. So that simply means that if you take any two distinct elements in S, they should be orthogonal. Such a set is as orthogonal set. So for example, if you look at the standard unit vectors u1, e2, en with respect to the usual dot product, they are orthogonal set of vectors. In fact, each of this vector has norm 1, so such a set is also known as orthonormal set. Similarly, look at f1 is equal to 1, f2 is equal to x minus half, f3 is equal to x to the power 3 minus 3 by 2 x square plus 3 by 5 x minus 1 by 20, and f4 is equal to x square minus x plus 1 by 6. You can check that this is an orthogonal set with respect to the inner product defined on C01, which is inner product fg is equal to integral of fx into gx from 0 to 1. So it is easy to check that this is an orthogonal set. Similarly, look at set of these three vectors 1 minus 1 1, 2 by 5 3 by 5 2 by 5 minus half 0 half, and define inner product on R3 as inner product xy is equal to y transpose Ax, where A is this matrix. This is symmetric positive definite matrix. This we have dealt with, this example we have dealt with earlier. So you can check that this given set of vectors are orthogonal. So let us check that. So define a matrix A and inner product, this we have done already, and three vectors u1, u2, u3, and let us check inner product A of u1 with u2, u1 with u3 and u2 with u3. It should be all of this should give you answer 0, that is correct. So these three vectors with respect to this inner product are orthogonal to each other, and therefore this set of vectors is an orthogonal set. Similarly, you can check the previous one. So I will leave that as an exercise. You can also verify the Pythagoras theorem. So in case you have just a second. Suppose you have vectors u1, u2, un which are orthogonal to each other, and then if you look at, for example, u2 plus u3, the norm square, this is same as norm of u1 square plus norm of u2 square. This is if u1, u2 are orthogonal, u1, u2 forms a right angle triangle. So this says that hypotenuse square is equal to base square plus height square, and you can extend this to three vectors u1, u2, u3 norm square is equal to u1 norm square plus u2 norm square plus u3 norm square, and you can extend this to any set of finite vectors. So this is only for the finite set of vectors. Let me put here I is equal to 1 to n. So here also I is equal to 1 to n. So this is n is any natural number, right. So let us try to verify this Pythagoras theorem for the above example, where you have u1, u2, u3 and in R3, and this is the inner product. So let us define u to be u1 plus u2 plus u3, and define the norm of u square, is it equal to norm of u1 square plus norm of u2 square plus norm of u3 square, you should get answer true, that is correct. So, this we have verified this for 3 vectors, but you can generalize this to any finitely many orthogonal set of vectors. Now, let us look at, suppose you have S which is an orthogonal set, then one can show that this is a linearly independent set of vectors. This is S is linearly independent. So, any orthogonal set is linearly independent. And let me define, in case you have orthogonal set of unit vectors, then we say, since it is going to be orthogonal and unit length, we call such a set as orthonormal set. And in case you have an orthonormal set which is also a basis of the inner product space V, then such a basis we call as orthonormal basis. Now, what is advantage of having an orthonormal basis? Let us just look at. Suppose you have basis B containing V1, V2, Vn, an orthonormal basis of an inner product space V. Then if you take any vector V, we know that V can be written as linear combination of V1, V2, Vn, and in that case these scalars, if V is summation alpha I Vi, then alpha I can be obtained as inner product of V with Vi. That is quite easy to verify, because you can just take inner product with V on both sides, and then you can check that, take inner product with Vi on both sides. On the right hand side, Vi inner product with Vj will be 0 when I is not equal to j. So, only surviving term will be alpha I, and alpha I is V inner product with Vi, and this is true for every I. And not only that, norm of V square will be summation alpha I square. So, that is the advantage. In case we have an orthonormal basis, then finding coordinate of any vector with respect to that basis is quite easy. All you need to do is, you need to take inner product of the vector V with the ith coordinate of the basis vector. So, that is the advantage. This is what exactly we had for standard basis in Rn. So, if you have any vector x which is summation xi ei, then xi is nothing but x inner product with ei, right. So, now the question is, how does one find an orthonormal basis? Having orthonormal basis helps, but can we find an orthonormal basis? We have seen how to find a basis. Starting with any non-zero vector, we can extend that to a basis of a finite dimensional vector space. However, how does one find an orthonormal basis? So, this is again easy. So, let us start with R2. So, in R2, suppose you start 2 linearly independent vectors, that is easy to find. And then what we can do is, we have seen that when we take orthogonal projection of a vector onto another vector, that gives rise to a vector which is perpendicular to a given vector, right. So, we will use that idea. So, I have 2 vectors, let us say u1 and u2, then define v1 is equal to, let us say, u1, and v2, what you do, you from u2 you take out the orthogonal projection of u2 onto v1, take out orthogonal projection of u2 onto v1, and then let us define q1 to be v1 upon norm v1 and q2 to be v2 upon norm v2. You can just check that these 2 vectors are orthogonal to each other. This we have already checked it, but we only thing here we did was we made this as unit vector. Now, let us try to plot graph of this 2 vectors u1 u2 which was given to vectors, and q1 q2 which we have obtained as orthonormal vectors. So, you can see here, this is actually u1, this is u2, and v1 we took as u1 divided by norm u1. So, it is unit vector along this direction, and this is if you take the perpendicular of u1 onto u2 and then u2 onto u1 and then take out that orthogonal component, this is what you get, this is your q1, right. So this is how we can generate two set of vectors which are orthogonal to each other and also they are of unit length. Once you generate orthogonal set of vectors, then you just need to divide by its length to make it orthonormal. So let us extend this in R3. Suppose I have 3 vectors u1, u2, u3 in R3. Now we will do this the same thing. Again we start with v1 is equal to u1 and v2 is a vector. How is it obtained? Again it is exactly in a similar way as we obtained v2 in the previous case. So from u2 you take out the orthogonal component of or orthogonal projection of u2 onto v1 and then how do you define v3? v3 to define v3 from u3 you subtract orthogonal projection of u3 onto v1 and also subtract orthogonal projection of u3 onto v2 and then define q1 is equal to norm v1 upon norm v1, q2 to be v2 upon norm v2 and q3 to be v3 upon norm v3. Let us look at what are these 3 vectors. You can check that these 3 vectors are orthogonal to each other and they are of unit length. Now again let us plot graph of these vectors, the graph of u1, u2, u3 along with the orthonormal set of vectors that we have obtained. So in this case you can just check, let me rotate little bit this. So this may be u1, this may be u2 and you have taken orthogonal projection of u2 upon u2 onto u1 and then you have taken out. So you have got this as this is your v1, this is your v1 upon norm v1 and this is v2 upon norm v2, this is v3 upon norm v3. So this is q1, q2, q3 and so what you can see here, this the plane which is shown is plane spanned by u1 and u2 and the vector q3 is perpendicular to this plane. So this is how you obtain 3 vectors which are orthonormal in R3 and you can extend this idea to more vectors. So for example if I take 4 vectors 1 x, x square, x cube, x4 in the set of all polynomials of degree less than equal to 4 with respect to this inner product, we can extend this idea. So first let us define inner product and the projection and the norm of vectors with respect to this inner product and then let us define f1, f2, f3, f4, f5. These are 5 set of vectors. This forms a basis of P4R. And then again the idea is similarly define G1 equal to F1, G2 is equal to F2 minus orthogonal projection of F2 onto G1, G3 again in the same way, G4 and G5. So in general what is GK? GK is defined as from Fk you take out the orthogonal projection of Fk onto all the previous orthogonal set of vectors that have been obtained. So let us execute this and let us also try to plot graph of this function. So let me first show what are these functions which are obtained, 1 x minus half, x to the power 4 minus x cube and so on. These are the vectors. One can check that these are orthogonal set of vectors with respect to this inner product. Let us define now unit vectors. So divide each of these G1, G2, G5 by its norm and then these are the vectors we have got. So this is an orthonormal set of vectors and then let us also plot graph of all these functions. So this is a straight line is h1 which is a constant function 1, h2 will be some kind of a straight line and h3, h4, h5. This is how these vectors these orthonormal set of vectors looks like. right. Now this you can actually extend this to uh, any finite dimensional inner product space, and this process is what is known as Gram-Schmidt process. So what is this? It says that if you start with any set of vectors v1, v2, vn, a linearly independent set of vectors which forms a basis, in particular take any basis v1, v2, vn of the finite dimensional vector space, inner product space V, and then you can find an orthonormal basis q1, q2, qn. And how do we obtain? So the process is exactly similar. So you start with u1 is equal to v1 and then define uk to be vk minus orthogonal projection of vk upon ui, I going from 1 to k minus 1. So what we are doing, we are throwing out orthogonal projection of v of uk onto all the previous orthogonal set of vectors that we have obtained, and then define qi to be ui upon norm ui. This is what is called Gram-Schmidt orthogonalization process. And this is quite simple. We already did it for 2 vectors, 3 vectors, 4 and 5 vectors. So let us create a user defined function for this, create a Sage subroutine for this. So how do we do that? So let us work with the standard inner product in Rn. So we have the the projection of a vector v onto u, which is v dot u divided by norm of u square into u. So that is the orthogonal projection. Next let us create Gram-Schmidt orthogonalization process subroutine. So what we are doing, we have to pass a set of vectors which are linearly independent, and define n to be the length of this set, that is number of vectors in S, and then initialize E is going to be the set of orthonormal vectors. So first let us define unit vector which is the first vector in S, initialize that as first vector in E, and then what we do, run a loop for k going from 1 to n. That means it will start from actually the second vector in S, right. So what is it? Define q2 to be sk, which is kth element in S. From that you take out the orthogonal projection of sk onto ei, where I going from 1 to range k, that means k minus 1, I going from 0 to k minus 1, right. So that is what is this loop, and then append inside A the unit vector, that is q upon norm q. And here just I am saying that the display only 5 digits because this is going to convert into float, right, and then return E. So that is a very simple user defined function for Gram-Schmidt process. And of course if you want to extend this to arbitrary inner product space, you may include the inner product with respect to which this orthogonal projection has to be taken, right. So that is quite easy. Now let us look at an example. So let us take this 4 vectors in Q4 or in R4, and then let us define these vectors v1, v2, v4, and L is equal to list of v1, v2, v4. We can check that this vector set of vectors v1, v2, v4 are linearly independent, and hence it forms a basis of Q4. Now let us call this Gram-Schmidt function which we have created and apply this to set of vectors L, and what we obtained is again a list of vectors L1, and so this is what we obtained. And then let us create a matrix out of this. So this is set of matrix. The first column is first element in this L1, second column is second element, and so on. And this matrix, if you look at this matrix, this is actually a matrix whose columns are orthonormal set of vectors. Such a matrix is known as orthogonal matrix. So any matrix Q in which all the columns are orthonormal set of vectors, then we say that such a matrix is orthogonal matrix. And in case you have orthogonal matrix, and then if you multiply that matrix with its transpose, you will get identity matrix. So of course this should be square matrix here. Right. So let us check that. So let us we can very easily check here this Q in ML into ML transpose, ML times ML dot T, this should give identity matrix. Okay, of course here these things are almost close to 0. So the off diagonal entry is of the order 10 power minus 6, because here there are a lot of round of error, so it has some error, but you can see here this is diagonal entry is 1 1 1, this is also close to 1, right. Next let us look at there is an inbuilt function to find Gram-Schmidt orthogonalization process. So suppose you define a matrix which is a column matrix of the set of linearly independent vectors. So that is we have already defined what is L. L is set of linearly independent vectors V1, V2, V4 in this case, and define A to be column matrix over QQ bar. So it is extended rational field, you can define over RDF and CDF also, and then call A on A transpose T, let us apply Gram-Schmidt, Gram underscore Schmidt, and this gives you actually two matrices. This gives you two matrices, output is G and M. I have stored this and G and M. So in this case this is G and this is M. M is lower triangular matrix if you look at, and if I take the transpose of each one of these, let us say transpose of this, define this in Q, and transpose of this define this is in R, and then this is what we get, these are the transpose. And not only that, if you try to multiply these two, this to Q into R, multiply Q into R, Q is this vector which was transpose of what we got using QR using Gram-Schmidt, and then when you multiply this you will get this matrix A. This is was the matrix A. If you look at, let me just also print what is this matrix A. So print A, right, so that both are the same. So Q into R is A. This also known as actually QR factorization. So here Q, though it is not an orthogonal orthogonal matrix, but this is set of orthogonal vectors, not orthonormal, right. However, one can define what is called QR factorization, and the QR factorization can be obtained using Gram-Schmidt process. So let us see what it is. So it says that if you have any matrix Q, any matrix, let us say A, it could be even square matrix, any rectangular matrix, or even non invertible matrix. So let us write A as column A1, A2, An. Then it says that there exists an orthogonal matrix Q and an upper triangular matrix R, such that A can be written as Q into R. Now suppose Q, if I say that Q1 it is given by column matrix Q1 to Qn, and R is given by R11, R12, R1n, 0, R22 and so on, then you can easily multiply these two matrices Q and R and then equate both sides. You will what we will get, the first, when you multiply this by first column, you will get R11 times Q1 is equal to A1, and if Q1 is orthonormal, you will get what should be R11. R11 will be nothing but norm of A1 upon norm of A1 actually, right. Similarly, multiply this by second column, what we will get is R12 times Q1 plus R22 times Q2 is equal to A2. Since we then, and since Q1, Q2 are orthogonal, if you take inner product of both the sides with Q1, you will get value of R11, and that will be inner product of A2 by Q1. Similarly, if I take inner product of this whole thing by Q2, then this will vanish, we will get R22. So and you can continue this process. So in general what you have is summation Rij times Qi, I going from 1 to j is nothing but Aj, that is jth column of A is product of this multiplied by jth column of this R, and from this you can take inner product of both the sides with Qi, you will get Rij. So you can obtain Rij. So once you have obtained this Q1, Q2, Qn, which we have already did in case of Gram-Schmidt process, then this Rij can be obtained using this formula, and this is what is known as Qr factorization, which is very useful concept. So let us see what is it. So once you have obtained this is just a repetition. So this once you have just obtained A is equal to Qr, then Rij is given by this. So let me just get rid of this part, this is just a repetition, right. And then next let us look at how we can obtain this Qr factorization. Okay. So this is the again the same set of vectors, and A is column matrix this, and then we can obtain this Gram-Schmidt process. So this is the column matrix of the Gram-Schmidt orthogonalization process. This is what we did already earlier, and then let us define R is equal to Q transpose A. You see that Q is orthogonal matrix, so Q into Q transpose will be identity, therefore Q transpose is nothing but inverse of Q. So once we have obtained Q, we can obtain R by taking the Q inverse times the matrix A. And you can also obtain this Qr factorization using inbuilt function, this is known as Qr. So define a matrix A which over Q bar, and then obtained Qr factorization of this, and this again will give you Q and R. So store this in Q1 and R1, and if you multiply Q1, let us see what is R1. This is R1, which is upper triangular matrix, and diagonal entries will be non-negative in this case. And then let us you can check that Q1 times R1. Let us check Q1 times R1. This should give you the original matrix. Okay, of course it gives you in decimal because these computations are numerical computations. So this when you say for example this is 0, question mark says that it is a kind of approximation, right. So and you can find Qr factorization of any matrix. For example, even you can have a singular matrix, factorization of a singular matrix. So here what is it? This is 3 cross 3 matrix starting from 0 to 9. So 0 1 2 3 to 0 1 2, the first row, second row is 2 3 4, third row is 5 6 7. So and you can find Qr factorization of that as well. So in this case you can see what are Q and R. So let me print Q and R. In this case this is what you get, right. So it is not necessary that the matrix A has to be singular non-singular matrix. Okay. Now you can also have a matrix which is non rectangular matrix. This is, I should write rectangular. You can have rectangular matrix, need not be square matrix. So if I have rectangular matrix, let us say this is 3 cross 4 matrix, again you can find its Qr factorization using inbuilt function A dot Qr, right. Next you can take help on Qr factorization. So if you have a matrix A and then say A dot Qr double question mark or single question mark, you will see a help document, and that help document you can go through along with the examples, and then see how you can make use of various options. Okay, this is the Qr factorization source code. So it also gives you the source code, and here there are several examples. You can see here this is a bigger example So, it is actually 5 cross 5 matrix, and it can also find Qr factorization of complex matrices. So, that is what it says, and so on. So, there are different examples one can go through this list of examples, and at the end let me leave you with a few exercises. These are quite simple exercises. So, first take a matrix A, define inner product with respect to this matrix, and then use Gram-Schmidt orthogonalization process to find an orthonormal basis with respect to a standard basis E1, E2, E3. Similarly, define an inner product on P3, P3, this I should write P3x instead of x, let me write here. P3R, and with respect to standard basis 1 x cube, again find an orthonormal set of basis, and then find Qr factorization of this, and hence solve this Ax equal to b. See, once you have Qr factorization of a matrix, then this system Ax equal to b can be written as Qr times x is equal to b. Now, Q is invertible, so if you multiply both sides by its inverse, that will get R times x is equal to Q transpose b, and then what you have R times x. So, R is upper triangular matrix. So, you actually to solve this system of linear equation, it has boiled down to solving upper triangular set of linear system, which is quite easy to solve using back substitution. Of course, this may be more expensive than a Gaussian elimination method. However, once you know the Qr factorization of this coefficient matrix, then it becomes easier to solve. Okay. So, these are a set of exercises. We will look at some more concepts in next lecture.